welcome to this morning session. So thanks for being here. Seems quite some people are still asleep, but that's fine. Let's welcome our first speaker, Hernan Larralde. The title is already on display. Looking forward to your talk.
Thank you very much, Rainer. Good morning. Thank you for being here. I know it's early. And after last night's nice dinner, it's actually hard to be here, as it's relatively obvious by the amount of people that made it. So I really appreciate your effort. And also I'd like to thank the organizers for inviting me to this event and the stay here. It's been very interesting. So thanks a lot. Let me begin. I'm going to talk very little about maxima and minima, but mostly a little bit about some statistics of a family of correlated variables. This is work that was done with Satya Mahundar sitting there and still hasn't fallen asleep. If you have any questions, please ask him. Greg Scher and their student Marco Vidoli. And later, I received help by a postdoc in Mexico called Roberto, who's now in Italy with Mantegna. We're about to move over there. I just realized right now that I made a mistake spelling Scher's last name here. I'm sorry. The details of our results, you can find them in these couple of papers from it's actually relatively recent work. So what I'm going to talk about, let me begin with a little actually simple background, which I'm sure you all know, is that for independent identically distributed random variables, there's a handful of universal distributions that describe a lot of their statistics. So what am I talking about? Of course, the central limit theorem is one of such universal results, pertaining to the sum of IID variables, and the Fisher-Tippett-Gnedenko theorem, which describes the statistics of the extreme values of a set of independent identically distributed variables. The extreme values refers to the largest statistics of the largest value of the set, or the smallest value of the set, doesn't matter. Specifically, I'm sure you all know, we have a large set and much greater than one independent identically distributed variables drawn from a common distribution phi with characterized by a mean mu and a variance sigma squared, and we define zeta as the sum of these variables. Then zeta is described by a Gaussian distribution with mean mu n, where n is the number of variables, the number of steps, if you like, if we thought of this as a random walk, and the variance also scales with n in the limit of very large n's. And of course, there are many generalizations of this theorem. Most notably, perhaps, is what happens when the common distribution from which the variables are drawn phi has a power law tail, so that its variance diverges. Then, of course, the Gaussian version of the central limit theorem doesn't apply, and the sum of these variables tends to a Levy alpha stable distribution. Okay, and then there are many other generalizations of this. On the other hand, the Fisher-Tippett-Gnedenko theorem refers to the statistics of the maxima. or a minimum, it doesn't matter, of a large set of independent identically distributed variables, all of them again drawn from a common distribution. And what it states is that for any set, or basically any set of such variables, there exists scaling factors A and B as a function of the number of steps, these scaling factors, such that shifted and rescaled cumulative distribution, G of C, right? So if we define a new variable, which is a shift and rescaling of the maximum value, we choose these AN and BN appropriately, then the C has a cumulative distribution, which is only one of these three. There's only three possibilities, no? Depending on the behavior, the tail behavior of the common distribution of these variables. So the only possibilities is that it's a gumball distribution, a Freche, or a Weibull distribution. So that's it. I mean, there's just a handful of universal distributions that describe these sets of independent identically distributed variables. It's Gaussians for their sum, or alpha stable distributions, and one of these three for their the maximum or minimum values. It doesn't matter, right? Now, what happens if instead of having independent variables, we have what perhaps we can call weakly correlated random variables? So we have like a sequence of random variables, and we assume that their correlation function decays quickly over a correlation length, say psi. It can be exponential, or I mean, it doesn't really matter the form. The whole idea is that as two variables become separated over a length much larger than the correlation length, then those variables are essentially independent, right? I mean, that's what this says. No? So if we have enough of these variables, much larger than this length scale, which is also larger than the correlation length, then the whole idea is that we can divide this set into n prime blocks. Each block containing n over z variables, and these variables, since they are very far from the variables in the neighboring blocks, then the variables in each of these blocks are essentially independent. Then it's actually very, it's easy to convince yourself that if we define by yi the maximum value of the variables inside one of these blocks, the ith block, then the maximum over the complete set of variables coincides with the maximum over the maximum in each block. But now these are independent variables, so the distribution of the maximum will fall into one of the three distributions of the Tippett-Nedenko theorem. And if we define Si as the sum over the variables in each block, then the total sum over the complete set is, of course, the sum of these SIs. But now, again, these SIs are independent, so this will be the sum of or large enough n, a large number of independent variables, And therefore, the distribution of the sum will fall into one of the forms of the central limit theorem. So that handful of universal distributions describes both independent variables and weakly correlated variables. They are all described by the same set of universal distributions. Okay. So what happens with strongly correlated random variables? What do I mean by strongly correlated? It means basically and intuitively that the correlation between the variables extends over the whole set of variables. So the idea of separating the set into uncorrelated blocks doesn't work. Okay? That's the basic idea. And for these kind of variables, there is no general theory to describe their extreme values, their sum statistics, their order statistics, etc. So, in the absence of a general theory, what one should try to do is study exactly solvable special cases in the hope of gaining some insight to this. No? So that's what we set out to do. Oh, this is the background. So let me show you a couple of cute, I think they're cute examples. Let's look at this joint probability distribution. Imagine we have a set of n random variables, real positive random variables, and they are distributed according to this joint distribution. Now, it's very clear, I think, that that the distribution does not factorize, and thus these variables, if they have this joint probability distribution, they are not independent, okay, at all. So, however, it's actually really easy to convince oneself that the cumulative distribution of the maximum value of this set has this form, right? The scaling form in the limit of large n. And not only that, we can also calculate the distribution of the smallest of these variables, and it has this exact form. It's not even approximate, this exact expression. And also, we can calculate the statistics of the sum of these variables, and it is given by this expression, which you notice has a long tail, not the same as this, has a long 1 over y squared tail, and it doesn't look like a Gaussian. It's not an alpha stable distribution. It's what it is. That's the distribution of the sum of these variables.
Can I ask a question?
Mm-hmm.
I understand, of course, that the variables are correlated, but how do you quantify the correlation here exactly in this case? Because before you show the exponential or something else,
Mm-hmm.
how do you quantify the correlation here?
Well, if you calculate like the correlation between any two of these variables, you'll find that it doesn't depend, obviously, does not depend on the distance between them, right? The correlation between any pair of variables is constant, no, throughout the whole system. Okay, it doesn't decay, doesn't grow, it's constant. Yes?
I have one more question. Is it true that the sequence is consistent? I mean, if you take n plus 1 real variables, then the first n has this distribution.
No.
So actually, x1, x2, xn, and if you take x1, x2,
So-
xn plus 1,
Actually, in this case, yes, I think it does have a distribution. In this case, not in the next example. But I think that if you take the marginal over one of these variables, you'll get the same distribution, yes. In this case. So this is a simple example of a strongly correlated set of variables for which you can calculate everything. A different example is this ugly distribution. Now we consider these x's are real variables, they're not positive real variables, but real variables, and we consider this joint distribution function here, where mu is again as before. I don't know if I mentioned it, but mu is a positive constant, and k here is a modified Bessel function. Mu appears here. Okay, and for this set of correlated, I mean, how do I know they're correlated? They're not independent, right? At least in that sense, they are strongly correlated. But again, one can actually calculate relatively easily the distribution of the maximum of this set. The minimum, I mean, this distribution is symmetric, so the minimum has a similar form, not worth calculating. But it's actually easy to see that in the limit of large n, the cumulative distribution function is given by this expression. And not only that, we can calculate the distribution of the sum of these variables, right? If we denote by y the sum of these x variables, then it turns out that it's a double-sided exponential. It's a very simple function. And so we have these two examples of correlated variables that can be solved completely. Oh, I will. So the question is, I mean, something is fishy here, obviously. Why are these correlated variables easy? I mean, what makes them easy? And it turns out that the answer is very simple, somewhat trivial perhaps, and it's that both these distributions are indeed strongly correlated, but they are both instances of conditionally independent random variables. That's the whole trick, right? The idea is that we can think that there exists a parameter, which we'll take as a random variable lambda, such that if we fix that parameter, then the set of variables are independent, okay? So their conditional probability, condition on a value of lambda, is a factorizable distribution, and then we integrate over lambda, okay? And this gives rise, of course, to correlated random variables in the sense that the resulting distribution is not a product distribution. So the examples I gave were these simple cases. Now, if this conditional distribution is taken to be an exponential with rate lambda, and we assume that lambda itself is also exponentially distributed with rate mu, we put these two things in here, we get this joint probability distribution. By the same token, if we consider these conditional distributions to be Gaussians with variance lambda, and we assume the variance is again exponentially distributed with rate mu, then the resulting variables are distributed according to this joint probability distribution, which is no longer a product distribution, so these variables are essentially strongly correlated. So this simple form allows us to do everything, right? It's more or less clear what we have to do. And we can calculate the bulk order statistics, not only the largest and smallest, but like what is the distribution of the 17th largest value? Sure, you can calculate the whole thing, at least in the limit of large n's, of course. We can calculate the extreme value statistics, which almost always coincides with the bulk order statistics at the extreme values, except in one of the cases we have to be a little bit careful. And we can calculate the sum of these variables very easily. Now, since this is a meeting on diffusion, then I'll concentrate on this, on the results for the sum statistics. No? So we assume now that these conditional probability distributions are characterized by an average mu and variance sigma. And of course, note that these quantities, the average and the variance, may be functions of the parameter lambda. And if we define again S as the sum of the variables, then we find that the distribution of this sum is given by this ugly expression here, where phi is the distribution of the parameter, mu prime is the derivative of the mean with respect to lambda, as long as that derivative is not zero. And these are evaluated, this is summed and evaluated over the solutions of this equation here. Okay? So you solve this equation, you plug it in here. That's where the S comes in and the N comes in, and these guys are function, lambda star is a function of S over N. So that's the asymptotic form of the distribution for the sum. And one can easily calculate like the moments of the distribution. These are given by this expression here. Notice they have what's usually called ballistic scaling, in the sense that the nth moment, moment scales like the nth power of the number of terms in the sum, which would be like the number of steps given by the random walk, if you like, times the mean of the distribution to the nth power averaged over the phi. And these results apply to the case in which, of course, the mean value depends on lambda. This is different from 0. If instead we have that the mean is equal to 0, I know, okay, so in this case, it's easy to show that distribution scales in this way, and that's it. No. If instead we have that the conditional distributions have mean 0, then there's no general expression for the distribution. One has to calculate this integral. It's more or less clear where it comes from. And the form of this integral, of this distribution, will depend strongly on what you put here, if you want to evaluate this integral. One can calculate the moments for large n again. It turns out that, of course, since the distribution is symmetric, the even moments are 0, the odd moments are 0, the even moments are given by this expression here. But where now we have this term sigma to the 2n averaged over phi, and we have what is known as diffusive scaling. The 2nth, so for example, the second moment scales linearly in the number of steps in the number of terms in the sum. Okay, and the distribution function, we can't calculate it exactly, or actually we can it depends on what choice we put here, but it's easy to see that it has this simple scaling form always. So in that sense, I think we can consider the sum as a mildly anomalous, because even though it has diffusive scaling, the limit distribution is not a Gaussian. So we have the sums of variables that scale like diffusion, but give strange limit distributions, not Gaussian distributions. Also, in that sense, they're outside the central limits here, of course. So let me show you a very simple application where of these ideas. No? So this thing here is real data again. These are the returns of Apple stocks measured every minute over a period of many years. How many years are there? Almost 18. And the first thing that's relatively clear is that these are not white noise, right? The other thing is that one can see is that the distribution is pretty symmetric, and that the regions of high fluctuations in the returns are like clumped together. So here we have like a period of 1 year of strong fluctuations. Here we have almost 8 months. Here we have a period, a few months with very small fluctuations, right? Again, here we have a period, a season of small fluctuations, followed by a season of very large fluctuations. In finance, instead of calling them fluctuations, they call it volatility. So what we notice here is that there is regions of high volatility and seasons of high volatility and seasons of small volatility. Now, if instead of the returns per minute, we are interested in returns over a time interval, say 10 minutes, an hour, or something like that, which are timescales many investors are interested. No, not everybody wants to invest for 18 years. Then we are interested in calculating the total returns over timescales that are much smaller than these clusters. Okay? And so we can calculate now, or what we did is calculated the returns over different time periods from 1 minute to about a day, I think. And of course, if you calculate the returns in this time, you'll get a different result than what you get if you calculate them in this time. So we calculated these returns. What the efficient market hypothesis tells us is that the returns are just basically a random walk. You know, the economists love saying that they invented diffusion before physicists did. It's true, Bachelier basically considered the returns as a random walk, and so we just add these variables over different time scales. But, and if we actually make the histogram of those returns, we get this ugly graph. No? These ones here are this is the distribution of returns over the 18 years, 1 minute returns, 10-minute returns, 30-minute returns, and so on, up to the returns over periods of 24 hours. Are those ones up there. Okay, so the idea then is that these returns correspond to sums of variables, of these variables, right, over short periods of time. And in each period of time, you'll have a different volatility. That means you'll have a different variance, okay? So we expect that the returns will be a sum of the variables, and the distribution of these sums should have this scaling. So let's see what happens. Now, this is the rescale plot of the data I just showed you. So it's not a perfect data collapse, but it's what it is. This is the real data. We get a pretty good data collapse according to what the theory says. Now we can do even more. No, we actually calculated the daily volatilities, which is basically what we did. Well, Roberto did is calculated the variance of the signal I showed you, but over windows corresponding to 1 day. And he would get different volatilities which correspond to different variances of the random walk. So this should be like a random walk with distributed variances, and the variances have a relatively acceptable power law tail with slope 3.5, and so we check what the theory says. No, we have here a distribution that has a power law tail, and you'd expect that the distribution of the sum will have a power law tail with the same power. So that's what the theory says, and this is what the data gives. Now this is the same slope as before, and we see that the tail is indeed well described by this power law as expected. And it looks nicer if we don't do a log-log plot. This is the power law, and these are the data. So that's pretty good, I think. And a different example is here. Now these are not Apple stocks, but rather it's Bitcoin. But we only had data for the daily returns, not the minute returns. Roberto promised he would do the minute returns, but hasn't done it. It looks definitely looks different, qualitatively different from this one, in the sense that fluctuations are, the volatility is different, has a different distribution than this one has. But still, we can see that there's volatility clustering, meaning that the volatility in this season is much higher than in this season. This season has low volatility, this season has very high volatility. So once again, if we try to calculate the distribution of returns over, here we only had over 2 days. These are the raw data, and this is the rescale data for 24-hour returns and returns over 48 hours, these are 2 days. And you get a reasonable rescaling, but please note that you have a double-sided exponential distribution. So it looks very much like the results we showed in the second example. if one plots the distribution of volatilities, we have very poor data, because we have only the daily returns. So if we do volatilities over larger periods, then we have very few data. If we do it over smaller periods, well, this is already the variance over 7 data points. It's not much. I'm not sure if that's an exponential distribution or not. These are certainly outliers, whatever they are, but as the real data, it doesn't look like a power law, and we need to do these calculations with finer data. So that's it. Conditionally independent random variables are a very simple generalization of independent identically distributed variables, and that's what makes them easy to analyze. But they are not independent. They are strongly correlated. And they appear in, these kind of, or this family of variables is huge, right? You can put any conditional probability and then distribute a parameter with whatever distribution you want, and you'll get a family of correlated random variables that can be easily analyzed. They appear naturally in sampling over heterogeneous environments. That's like the examples of the returns show, right, that this clustering of the volatility can be thought of as a very heterogeneous system, and if you sample over the system, you will get something that is well described by these kind of variables. They also appear in mean field theories, and in random matrix theories. Now, unfortunately, their order and some statistics depend crucially on the distribution of the parameters. So there are no simple asymptotic universal distributions to describe this family. One will get different laws for different distributions, and that's it. That's what I wanted to tell you. Thanks.
Thank you very much for being perfectly in time. So we have quite some time for questions.
How much of this depends on the random variables, both the x's and the lambda, being one-dimensional?
Nothing. You can do higher dimensional independently. Conditionally independent variables. You can do any dimension.
For the lambda as well? If lambda is...
Actually, in principle, yes, I guess you could. You could condition on several variables, which could be like the different components of lambda. And yes, you could perhaps have one distribution of variances and a different distribution of means. So you'd have two components. You could think of that as a two-dimensional vector or more. You can even have, but it's not very useful, a different component lambda for each variable, but then the correlations gets messy. But you can play with, if it's useful, you can play with much higher dimensional systems.
So Hernan, so when you said that there was a power law, that was like 1.5 order of magnitude, no? So it's,
Yeah,
so
I agree.
Couldn't you extend? I mean, especially the data on the, you stop at 24 hours, no? I think it was the Apple data. Yeah. Yeah. One.
Yeah, no, that's what it is. I agree. I mean, we just basically what Roberto did is calculated the variance over a day, no? Because you need several data, so a day has, since these are minute data, you have a lot of data, and then just calculated the variance and just plotted the histogram. And I agree, you can say, okay, that's not a perfect power law. You're right. It would be nicer if we had longer tail here, but Apple hasn't existed long enough. We need Apple to be to exist for longer.
So I was curious also, when you compute this quantity, so you slide through, so you have a chunk of data over time, and you just pick a window and you slide through, or you just go,
No, there's no overlap over
windows. You do no overlap.
No overlap. So we do windows of different sizes without overlap. That's why we can't go to very large sizes either, because we run out of data. This is all the data. There's no more. We tried it also in indexes and things like that. I mean, 2 examples are already one too many.
That's another one.
Have you tried comparing this with implied volatilities? So when you take an option, you get this kind of skew, right? This or smile, whatever they call it in finance.
We call it the smile, yes.
And that's quite nicely. That's what they use to calibrate things like rough volatility, where you have this sub-diffuse.
No, so the answer is no, we haven't tried it. We just basically said this is like, we'll just take this as a sequence of data, and there's really, if you notice, there's really no economic implication in what I said, no? So I'm afraid these kind of things cannot be used to predict finance or to value futures or anything like that. That would be neat. And it's not easy to find, like a minute by minute implied volatility or even dated. It's very hard to find. You have to buy it. If it's in finance, it costs money.
Okay, let's thank the speaker again.